Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the IIT JAM mathematics exam held in 2025. In this video, we discuss the solutions of 4 problems from real analysis, and these questions are related to functions of one real variable. And this is the part 2 of the video out of the 3 parts that is devoted for the functions of one real variable. These questions are suitable for all these examinations. Right. This is the question number 30 for 2 marks. It is a multiple choice question. The given question is the number of elements in the set consisting of x belongs to R such that 8x square plus x to the power of 4 plus x to the power of 8 is equal to cos x is equal to. We are given 4 options. Let's now discuss the solution of the problem in detail. We want to find the number of elements in the set consisting of x belongs to R such that 8x square plus x to the power of 4 plus x to the power of 8 is equal to cos x. Let us take that set that is equal to the set of all those x belongs to R, which satisfies the equation f of x is equal to 0, where f of x is taken to be 8x square plus x to the power of 4 plus x to the power of 8 minus cos x. That is the fx. That means we want to find the roots of this equation. Fx is equal to 0. Right. Observe that f of 0, that is substitute x is equal to 0, you will get 0 minus cos 0, that is cos 0 is 1 minus cos 0 is minus 1. Right. Now take its first derivative. F prime x is equal to 16x plus 4x cube plus 8x to the power of 7 plus sin x. Right. When x is negative, 16x is negative, 4x cube is negative, 8x7 is negative, and this will be 16 plus 4, 20, 20 plus 28, minus 28, and this will be negligible. So it will be altogether less than 0. Note that f prime x is negative for all x less than 0, and obviously for all x greater than 0 this will be positive. So f prime x is positive for all x greater than 0. That means in the interval minus infinity to 0 it will be a strictly decreasing function, and in 0 to infinity it is strictly increasing function. When it is a strictly decreasing function, decreases up to minus 1 and then increases, then while doing so it crosses the negative x-axis exactly once, and the positive x-axis exactly once. This implies f of x is strictly decreasing function for all x less than 0, then f of 0 is minus 1, and f of x is strictly increasing function for all x greater than 0. So therefore f of x is equal to 0 at some point a belongs to minus infinity to 0. That means it crosses the negative real axis exactly once, and f of x is equal to 0 at some point b belongs to 0 to infinity. That means it crosses the x-axis exactly once in the positive side, 0 to infinity. So right, so that means this will be almost looks like this, like parabola, right? And thus in this set we have only 2 points, namely a comma b. Therefore the number of elements in that set is 2. Therefore the answer to this question is 2. That is the option C. The answer to this question is option C, and that is the detailed discussion of the solution of this problem. We continue in the next slide. Right, this is the question number 37 for 2 marks. Multiple select question, MSQ. There can be more than one answer. The given question is, let f be a twice differentiable function from R to R such that f of 0 is 0, f prime 0 is 2, f of 1 is minus 3. Then which of the following is (are) true? We are given 4 options. Option A, mod of f prime x less than or equal to 2 for all x belongs to the closed interval 0 to 1. Option B, mod of f prime x1 is greater than 2 for some x1 belongs to the closed interval 0 to 1. So in options A and B, it talks about the first derivative f prime x. Option C, mod of f double prime x less than 10 for all x belongs to the closed interval 0 to 1. Option D, mod of f double prime x2 is greater than or equal to 10 for some x2 belongs to the closed interval 0 to 1. In options C and D, it talks about the second derivative, right? Okay, let's now discuss the solution of the problem in detail. We are given f from R to R, which is a twice differentiable function. This means f is continuous, f prime is continuous, and f double prime exists. Right. So given f of 0 is 0, f prime 0, 2, and f of 1 is minus 3. It talks about in A and B, its first derivative. Right. And now f of x is continuous in 0 closed interval 0 to 1 because it is continuous on the whole of R, therefore it's continuous on 0 to 1, and f of x is differentiable on 0 to 1 because the first derivative is continuous on the whole of R, therefore f of x is differentiable on 0 to 1. So we apply Lagrange's mean value theorem. Then by the Lagrange's mean value theorem, there exists at least one point x1 belongs to the open interval 0 to 1 such that f prime of x1 is equal to f of 1 minus f of 0 by 1 minus 0. Substitute the values and simplify, you will get minus 3. We want the modulus. So take the modulus. Modulus of f prime x1 is modulus of minus 3 is equal to 3. Greater than 2 for some x1 belongs to the closed interval 0 to 1. Sir, x1 belongs to the open interval 0 to 1. No problem. x1 belongs to the open interval 0 to 1 implies x1 belongs to the closed interval 0 to 1. So we can write this. So now at some point x1, mod of f prime x1 is equal to 3. Therefore, option A is not true. It says less than or equal to 2 for all x belongs to the closed and bounded interval 0 to 1, but here at some point it takes a value bigger than 2. Therefore, option A is not true, and obviously option B is true. Right. We continue in the next slide. Right, that's what we have. And we recall the famous Taylor's theorem with Lagrange's form of remainder. And this says if f is a real valued function defined on the bounded interval a comma b, f prime, f double prime, etc., n minus 1th derivative of f, they are all continuous on the closed interval a to b, and the nth derivative exists in the open interval a to b, then there exists a c belongs to the open interval a to b such that f of b is equal to f of a plus f prime a into b minus a plus f double prime a by 2 factorial into b minus a whole square plus so on and so forth plus n minus 1th derivative of a of f at a by n minus 1 factorial into b minus a to the power of n minus 1 plus the Lagrange's form of remainder is the nth derivative of f at c, where c belongs to, there exists at least one c belongs to the open interval a to b such that by n factorial into b minus a to the power of n. This is the Lagrange's form of remainder. We normally write Rn. Right. Now take this. We write for b 1, for a 0. That means we are talking about the closed interval 0 to 1. 0 to 1. So by Taylor's theorem, with Lagrange's form of remainder, with n is equal to 2, there exists at least one point x2 belongs to the open interval 0 to 1. For c, we have taken x2 such that f of 1 is equal to f of 0 plus f prime 0 into 1 minus 0 plus the Lagrange's form of remainder f second derivative at x2 by n factorial into 1 minus 0 whole square. Substitute the values of f of 1, f of 0, f prime 0. Then you will get minus 3 is equal to 0, 0 plus 2 plus f double prime x2 by 2 factorial. That is f double prime x2, f double prime at x2 by 2 factorial is minus 5. F double prime at x2 is minus 10. Taking the modulus of f double prime at x2 is 10. Is 10. So is exactly equal to 10. Option C says is less than 10 for all. No. For at some point x2, f double prime of x2 modulus is equal to 2. Therefore, option C is false. Option C is false. Therefore, this is so for some x2 belongs to the closed interval 0 to 1. No worry, x2 belongs to open interval 0 to 1 implies x2 belongs to the closed interval 0 to 1. So this is true. This is true. Therefore, option C is not true and option D is true. Why? Because it is greater than or equal to 10 is equal to 10 we got. So it is greater than or equal to 10 for some x2 belongs to 0 to 1 is true. Option D is also true. The answer to this question is options B. We have already seen option B is true. Option B and D. And it's a good example. Right. We continue in the next slide for the next question. Right, this is the question number 38. It's again multiple select question for 2 marks. There can be more than one answer. Let f be a twice differentiable function from R to R such that f of 0 is 4, f of 1 is minus 2, f of 2 is 8, f of 3 is equal to 2. Then which of the following is oblique R are true? We are given 4 options. Option A, mod of f prime x is less than 5 for all x belongs to the closed interval 0 to 1. Option B, mod of f prime x1 is greater than or equal to 5 for some x1 belongs to the closed interval 0 to 1. It is almost the same type of option what we have seen in the last question. Option C, f prime x2 is equal to 0 for some x2 belongs to the closed interval 0 to 3. Option D, f double prime at x3 is 0 for some x3 belongs to the closed interval 0 to 3. So now, first derivative, second derivatives, they are becoming 0 for some points x2 and x3 in the closed interval 0 to 3. Right. Let's now discuss the solution of the problem in detail. It is definitely takes longer time to answer this question. So we are given a function f from R to R, which is a twice differentiable function. This means to say f prime are continuous and f double prime exists on whole of R. Therefore, they exist on the closed interval 0 to 1 and 0 to 3, and those cases can be considered. Now, given f of 0 is 4, f of 1 is minus 2, f of 2 is 8, f of 3 is 2. Right. We concentrate on 0 to 1. So now f of x is continuous on 0 to 1, correct? F of x is differentiable on open interval 0 to 1, correct? Therefore, we use the Lagrange's mean value theorem. By Lagrange's mean value theorem, there exists at least one point x1 belongs to the open interval 0 to 1 such that f prime of x1 is equal to f of 1 minus f of 0 by 1 minus 0. That is equal to minus 2 minus 4 by 1 minus 0, that is minus 6. So x1 is in between 0 and 1. Right. Take the modulus. Modulus of f prime x1 is equal to minus 6. 6 is greater than 5. Greater than 5. For some x1 belongs to 0 to 1, no worry. x1 belongs to open interval 0 to 1 will imply x1 belongs to closed interval 0 to 1. And from this, option B is true. And it is less than 5 for all, but at some point x1, it takes 6, which is a bigger than 5 value. Therefore, option A is not true and option B is true. It is ditto the same question like what we have done in the last question. Right. What we have done, we have written f prime x1 is equal to minus 6 for some x1 belongs to 0 to 1. Right. Now, f of x is continuous in the closed interval 1 to 2 and differentiable in the open interval 1 to 2. Therefore, by Lagrange's mean value theorem, there exists at least one point A in the open interval 1, 2 such that f prime A is equal to f of 2 minus f of 1 by 2 minus 1 and 8 minus of minus 2 by 2 minus 1, that is 10. So, A is here somewhere between 1 and 2. So, now what I will see, now thus f prime A is 10 for some A belongs to open interval 1, 2. We have f prime is continuous because f double prime exists, therefore f prime is continuous on x1 A, x1 closed and bounded interval x1 A, and now f prime x1 is minus 6, it takes negative value for some x1 belongs to 0 to 1, and f prime A is equal to 10 greater than 0 for some A belongs to 1 to 2. And f prime is continuous. The product, if you take, it will be negative. So, we will use the intermediate value theorem. So, what intermediate value theorem says? Applying intermediate value theorem for f prime, there exists a point x2 in between x1 and A x1 and a such that f prime x2 is 0. So it will be somewhere between x1 and a. x2 is here. So therefore f prime of x2 is 0 for some x2 belongs to x2 belongs to the closed interval 0 to 3. Why? x2 belongs to x2 belongs to x1 comma a open interval. Open interval x1 comma a is contained in the closed interval 0 to 2 is contained in 0 to 3. Therefore x2 belongs to 0 to 3. So what is true? Option C. Thus option C is true. So it remains only option D. That we will discuss in the next slide. Right. Now we have only one option, D. And f prime x1 is minus 6 for some x1 belongs to 0 to 1. That is required for me. Now f of x is continuous on 2 to 3. Closed interval 2 to 3. fx is differentiable in the open interval 2 to 3. Use Lagrange's mean value theorem. There exists at least one point B in the open interval 2 to 3 such that f prime B is equal to f of 3 minus f of 2 by 3 minus 2. That will be minus 6. There is one B in between 2 and 3. Now what you see is f prime x1 is minus 6 and f prime b is also minus 6. So why not we consider the interval x1 to be it is continuous in the interval x1 to be, differentiable in the open interval x1 to be, and at the end points f prime of x1 is equal to f prime of b. Use Rolle's theorem. Thus f prime b is minus 6 and we have f prime is continuous in the closed interval x1 to b. F prime is differentiable in the open interval f1 to b, and f prime x1 is equal to f prime b is equal to minus 6 at the end points of the interval x1 to b. We can apply Rolle's theorem here. We apply Rolle's theorem. Then there exists, by Rolle's theorem, there exists a point x3 belongs to x1 comma b open interval such that f double prime x3 is 0. Right, by Rolle's theorem. So this is x3 is here. So thus, therefore, f double prime x3 is 0 for some x3 belongs to 0 to 3, open interval, closed interval 0 to 3, because the open interval x1 to b is contained in 0 to 3. So therefore, thus option D is also true. Summarizing all the options, the answer to this question is options B and C and D. That is the detailed discussion of the solution of this problem, and this problem will take a longer time in the examination. It is not a difficult question, but it takes more time. Right. We continue for the next question in the next slide. Right. This is question number 42, which is a numerical answer type question for 1 mark. Find the value of limit n tends to infinity 8n in brackets e power 1 by 2n minus 1 multiplied by sine of 1 by 2n plus modulus of cos of 1 by 2n inside the bracket is equal to. So you have to write down rounded off to 2 decimal places. take that. Limit of that is equal to limit n tends to infinity of 8n into in bracket c to the power of 1 by 2n minus 1 multiplied by limit n tends to infinity of sin 1 by 2n plus mod cos 1 by 2n. Limit of the product is equal to product of their limits. Agreed. Limit n tends to infinity of 8n into e to the power of 1 by 2n expansion we have written minus 1. Minus 1 and plus 1 cancels. Right. Into limit of the sum is equal to sum of their limits. Limit n tends to infinity of first plus limit n tends to infinity of second. 1 and minus 1 cancels. Then we will get limit n tends to infinity of 8n into 1 by 2n plus 1 by 2 factorial into 1 by 2n square plus the higher powers of 1 by 2n into limit of sin 1 by 2n is 0 plus limit n tends to mod cos 1 by 2n is 1. So this is 0 plus 1 is 1. Now in this you take 1 by 2n common. Limit n tends to 8n into 1 by 2n into 1 plus 1 by 2 factorial into 1 by 2n plus higher powers of 1 by 2n. Now 8n into 1 by 2n is n cancels, 8 by 2 is 4. So this will be 4 times limit n tends to infinity of 1 plus 1 by 2 factorial into 1 by 2n plus the higher powers of 1 by 2n. And that is limit n tends to 1 is 1, limit n tends to 1 by 2n is 0, all other terms will become 0, thereby 4 into 1 is 4. That's your answer. So it is to be written as 4.00. So the answer to this question is 4.00, and that is the detailed discussion of this problem. Because it's a numerical answer type question for 1 mark, therefore the answer obviously will be very less, and it will be straightforward. Right. So in this video I have discussed 4 problems from the functions of one real variable from the real analysis, and 2 of the questions we have used extensively Lagrange's mean value theorem, Taylor's theorem and Rolle's theorem, and these are the applications of those 3 theorems in those 2 problems. And I am sure that you have understood the solutions of these problems. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Yes, we will be definitely meeting you all, to discuss the third part of this video on functions of a single real variable from real analysis. I wish you all the best. Thank you.